Okay, we're going to continue talking about statistics today. But first, we're going to take a small sidestep, do an ACT prep question. This is from an ACT practice test from a few years ago. Test scores for a history test are shown below. What is the mean, median, mode, and range of this data set? So go ahead and pause this, take a minute, 90 seconds, and see if you can get these. Reminder that the ACT gives you 60 questions in 60 minutes. So hopefully you should be able to do this question in about a minute or less. So go ahead. Okay, first we have to understand what mean, median, mode, and range are. The range might be the easiest. The range is the largest number minus the smallest number. So if we're looking through this list, the largest number I see is 95. The smallest number I see is 40. So the range should be 55. The mode, kind of working backwards here, the mode is the most commonly occurring number. I only see one number that occurs twice. That's 91. The median, if you rank these numbers from highest to lowest, or lowest to highest, excuse me, the median is the middle number. So here they are rearranged from lowest to highest. This is also helpful if you're doing the range. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers. So if there's 11 numbers, there are 5 on each side of the middle number. So 1, 2, 3, 4, 5, 6 would be our middle number. So the median is 83. The mean is just the average. So we just need to add all of these numbers up and divide by the 11 numbers that there are. So 40 plus 62 plus 71 plus 72 plus 74 plus 83 plus 84 plus 90 plus 91 plus 91 plus 95. I get 853 divided by 11. Our mean or average 77.55, rounded to the nearest hundredth. Okay. Hopefully that was relatively easy. Let's get back into some stats. Why would we collect statistics and samples? We talked a little bit about this yesterday, but usually there's a question that we want answered, and that question can be literally anything. But to answer that question, we need to know something about a group of things, whether that be people or products or whatever it might be. We need to collect some data to analyze to answer the question. A parameter is a measure that describes a certain characteristic of a population. This is the value we want to know, but usually the population is so large we can't calculate it. For example, if we wanted to know the average height of males in the US, we would have to measure every single male. And then once we measured all the heights, added them up, and divided by the number of males in the United States, let's say the height turned out to be 5'10". The parameter would be 5'10", meaning the average height of all males in the United States would be 5'10". Kind of like we talked about before, it would be pretty difficult to measure every single male in the United States. So the parameter is often impossible to know, but that's what we're trying to describe. Instead, we use a statistic, a measure that describes a characteristic of a sample, which is then used to estimate the parameter. So instead of measuring every single male in the United States, we're going to sample 100 males randomly. How we come to that sample could be any number of ways, but we've selected 100, and we find the average of that sample. Let's say that the average height of those 100 is 5'9". That would be the statistic. So the parameter would be the average height of all males, where there's no way to actually know that. So we create a sample, we find the average height of the sample, and that is the statistic. Okay. So a stratified random sample of 30 registered nurses is selected from all hospitals in a 10-county area, and the median salary is calculated. What would the sample be? The sample would be the 30 registered nurses, 30 RNs. The population would be all registered nurses, but only from that 10-county area. If that's all I'm looking at, I can't say that this represents the entire country or the entire world. It would just be all the RNs, all the nurses from the 10-county area that we've looked at. The sample statistic would be the average or mean salary of the 30 nurses. And the population parameter would be the mean salary of all nurses in the 10 counties. Right? We probably can't know that because 10 counties worth of nurses, especially depending on what state we're in, could be a very large number of nurses. So this is what we find, and this is what we are trying to describe. It's what we want to know. It's just chances are it's going to be too difficult. Okay. An NFL team is debating between two running backs to draft for their team. The number of rushing yards from the past 5 games is shown below. Which one should they pick? So if you're not familiar with football, rushing yards are the number of yards that a player, usually a running back, maybe the quarterback, carries the ball for while they're running. So instead of throwing, just running with the ball. You add up all the progress you make for the whole game, and those are your rushing yards. So if the team is trying to decide between these two running backs, these are the number of yards that each running back carried the ball for in their last 5 games. So running back A went 75 yards, 80 yards, 85 yards, 90 yards, and 85 yards in his last 5 games. Running back B went 40 yards, 120 yards, 40 yards, 60 yards, and 160 yards. So what could we do with this information? Well, the easy one is probably to determine the average yards per game. So, you know, who carries the ball on average the farthest. We might also be interested in the variability, kind of like an average distance from the mean. So if you just look, you might have already noticed that running back A is a lot more consistent. Running back B is kind of all over the place. Sometimes he goes 40 yards. Sometimes he goes 160. 4 times as big, right? Option A is within, 15 yards the whole time from 75 to 90. This guy goes from 40 to 160, so he's all over the place. So there are ways that we can do this. Let's do the average first. So I'm just going to find the average of running back A's yards. So 75 plus 80 plus 85 plus 90 plus 85 is 415 yards. Divided by the 5 games, his mean is 83 yards. Option B, 40 plus 120 plus 40 plus 60 plus 160 is 420 divided by 5 yards is 84 yards per game. If that's all we were going off of, then this would be the one we'd want, right? He, on average, carries the ball 1 yard further. But you might see that that's not necessarily the only thing we care about, right? If there's only a 1 yard difference between these two, how many times is he significantly lower than this for option B? So if his average is 84, sometimes he is significantly lower than 84 yards. Sometimes he's significantly higher also, but sometimes he's way lower. He's just unpredictable. Option A, he's only 8 yards away, 3 yards away. Those are both minus. Then he's plus 2 yards, plus 7 yards, and plus 2 yards. This guy's minus 44, plus 36, minus 44, minus 24, and plus 76. So he's all over the place. So we might take into account the consistency. And we have a method in statistics for calculating more or less what you might describe as consistency. And it's called standard deviation. It's a calculation of how the data deviates from the mean. So mean meaning the average, right? And deviate meaning stray from or change from. There's quite a few steps to doing this by hand, but it's very doable. So first we need to find the mean, find the average. Then we're going to find the difference between each data value represented by x sub n and the mean. So I'm going to subtract each data point from the mean and then square it. We're squaring them to make them all positive. Then we're going to find the sum of all those values, add all of the things we found in step 2 up, and divide by the number. So we're kind of taking the average of the distance from the means squared, and then take the square root again. So we square it to make it positive at the beginning. We take the square root at the end to get back to standard deviation. So this is the formula. This is the Greek letter that we use to represent standard deviation. It's a lowercase sigma. mean minus the first data point squared plus mean minus the second data point squared. And you keep doing that until you get to the last data point squared. Divide that value by the number of data points, and then take the square root. So let's do one. Okay. This is the same football question, same running backs. I've got the formula written here so we can kind of see what we're talking about. Running back A, running back B, and their averages. So for running back A, we've got the mean minus data point A, which is 75 squared, plus the mean minus data point 2 squared, plus the mean minus the third data point squared, plus the average, the mean, minus the fourth data point squared, and finally the last one. So we should have 5 of these total because there's 5 data points. We're going to divide that entire thing by 5, and then, that's terrible, take the square root of everything. So let's do this. Here we go. 83 minus 75 is 8. 83 minus 80 is 3. 83 minus 85 is negative 2 squared, which would be just 4, right? 83 minus 90 is negative 7. And 83 minus 85 is negative 2 again. And we're going to divide all of that by 5. So depending on how much you want to do in the calculator, we could say, well, that's 64 plus 9 plus 4 plus 49 plus 4 divided by 5, which is, I'm going to do that on the calculator right now, 64 plus 9 plus 4 plus 4 plus 49 is 130 divided by 5 is 26. But remember, we have to take the square root of all of this. So we have to take the square root of 26, which is approximately 5.099 or 5.1, let's say. So what the standard deviation means is that for running back A, on average, he will run 83 yards. But he will also tend to deviate from that mean kind of by an average of 5.1 yards. So the larger the average, the farther he runs. The smaller the standard deviation, the more consistent he is. So we want the mean to be high and the standard deviation to be low. It kind of shows that the data is all very tightly grouped. Okay, so let's do the same thing for option B. I'm going to slide our data down so we can see what we're doing. I need to do 84 minus 40 squared plus 120 minus 40 squared plus, oops, sorry, this is 84. That was close. Always the average. Plus 84 minus, let's see, I've done the 240s, so minus 120. I'm doing this slightly out of order, I'm sorry. Plus 84 minus 60 plus 84 minus 160. Now we're going to square all of those values. That whole thing gets divided by 5 because there are 5 data points. And then we're going to take the square root of everything. So 84 minus 40, that's 44 squared. Plus another 44 squared. Then I've got 84 minus 120, negative 36 squared. 84 minus 60 is 24 squared. And then 84 minus 160 should be negative 76 squared. Divide all that by 5 and take the square root of the whole thing. If you want to be very careful, you could type all of this into the calculator all at once. I'm going to do it in steps. So I'm going to do 44 squared plus 49, oops, 44 squared plus 49 squared plus 36 squared plus 24 squared plus negative 76 squared. I get 433. can divide that by 5. And I have the square root of 86.6. So the square root of 86.6 is 9.31. So I'm just going to call it 9.3. So although running back B does run on average 1 yard farther than running back A, his standard deviation is quite a bit larger. If I were choosing these players, I would 100% choose option A. He's not that much far below option B in terms of the average. They're running basically the same amount, but he's far more consistent. You know you're going to get 83 yards out of option A most of the time. Option B, you don't really know how far you're going to get because he could be anywhere around 84, usually within 9 yards. So he's going to run, plus or minus approximately 10 yards most of the time, and obviously it could be even much farther than that. So running back B is far more volatile, far more inconsistent or unpredictable. For 1 yard of extra average is probably not worth it, at least in my opinion, and that would change depending on what the coach is going after, but that's just one way to check. Okay, so yeah, so this is kind of what we just talked about. You can also calculate the standard deviation on a calculator. Now I know that many of you do not have your own graphing calculator at home. Hopefully you can either use the emulator Wabbit EMU or some other free app emulator of a graphing calculator. It would absolutely be worth you getting on the App Store and looking for one. You can use Desmos.com. You could find a tutorial on that. There are other standard deviation calculators on the internet. Make sure you find something that will work for you because otherwise you could be seeing a lot of difficulties because we did this for 5 data points. What if I gave you 12 to work with or 37 data points? You don't want to do that by hand. Is it possible? Yes. It's ugly though. So on the graphing calculator, if you do happen to have one, or if you find an emulator for a TI 83, 84, 84 CE, whatever, any of the common Texas Instruments calculators, you're going to go to Stat, Edit. So you'll hit Enter on Edit after you hit Stat, and you'll find those lists, right? You'll want to make sure that it's list 1. You'll enter all the stats one by one. Then you'll go Stats. You're going to arrow to the right to that Calculate menu, and you're going to choose this one variable stats. This is exactly how we did linear regression when we were doing our doll drop lab. Exactly the same process, but when you get to the Calculate menu, instead of going all the way down to linear regression, you're going to go to one variable statistics, and it will tell you this first number, which is the average. This is the sum of all of the data points, not all that useful. This is the sum of all the data points squared, not all that useful. This is what's called the variance, and then the one at the bottom is our standard deviation. That's the one you would want. Obviously, I messed up doing it by hand because the standard deviation here is 48 yards, which does make a lot more sense. So I messed up somewhere doing it by hand. Hopefully you caught that and fixed it as we were doing it. But for option A, mean of 83, standard deviation of 5.1. That one we got right. Option B, mean of 84, standard deviation of 48, which makes more sense if you look at the data. He's, deviating from his average. Where did the list go? By a lot more than 9 yards. It's more like 40 yards at a time. So my apologies for getting that mixed up. I've got a yo-yo here for you to do. A soda company is choosing between 2 machines that will fill up their soda cans. They take a sample of 5 cans filled up by each machine. Each machine is attempting to fill the cans to 12 ounces. Which of these machines should they choose for their factories? So go ahead and pause this. Take 3 minutes or so. Find the mean and the standard deviation, and then come back with your conclusion as to which machine the company should purchase. Okay, hopefully you've done that. You have a mean and a standard deviation. Let's scroll here a little bit. These are the means you should have gotten. For machine 1, the average is 11.98, and for machine 2, the average is 12.26. Choosing right there, which machine do you think it should be if that's all we did? Should they overfill by a 1/4 ounce or underfill by 2/100ths of an ounce on average? Based on this information, I would think probably machine 1 would be better. And then after we find the standard deviation, though, we see that for machine 1, its standard deviation is 0.117 or 0.18. Machine 2 is only 0.05. This one is 2 times less than this one. So which machine should they choose, do you think? I would think you would want to choose machine 2 because you can adjust what the target is since it's far more consistent. Just bring down the target a little bit because it's overfilling right now. So adjust the machine and you'll get a much tighter grouping around where you want. Here, the average is pretty close to what they want, but they're going to be up and down all over the place because their standard deviation is larger. In this case, I would choose machine 2 and then just calibrate the machine to shoot for a little bit less so that this average comes down a bit. Because if a standard deviation is this small, you should be able to adjust where the average hits. Okay. Last one. The coach for the swim team is considering 2 different lineups for her relay team. Both tables below contain the times in minutes for each lineup. So this is lineup number 1's first trial, their second trial, their third trial. So each lineup, each relay team has done 10 different time trials. Which lineup should she choose to be the relay team? Okay. We'd want the mean and standard deviation. I'm going to say go ahead and pause this, find the mean and standard deviation, and then hit play again. Okay. Lineup A's mean is 4.354 with a standard deviation of 0.16, while lineup B has a mean time of 4.42 with a standard deviation of 0.16. So in this case, the standard deviations are exactly the same, right? Standard deviations are both 0.16. So the groupings are exactly the same in terms of their consistency. The difference is that the average times are quite a bit different. Since Team A has a lower average with the same standard deviation, definitely should be choosing Team A or lineup A because that team has a lower average time but the exact same consistency as Team B, which has a higher average time. Okay. Hopefully that makes sense. I would say moving forward from this point, you should make sure to have some option for a graphing calculator to find standard deviation with, whether that be a Texas Instruments calculator, a free emulator app, or some calculator you find on the internet. I would look into that. If you have questions about where you should be looking, or if you can't find one, shoot me an email, and I'd be happy to help. Good luck.